Here are 3 points in a room. Their positions are known, surveyed, to the millimeter. A camera photographs them, and I ask the computer, where is the camera? Here's an answer. I project the 3 points through it back into the image, and they land exactly on the measured pixels. 0 error. Solved. Except, here's another answer. A different position, a different tilt, more than a meter away from the first, and its reprojection is also perfect. And another. And another. 4 cameras spread over a meter of space, and every single one of them explains this photograph without a single pixel of error. The geometry isn't broken, it's telling the truth. With 3 points, all 4 of these are correct. Now watch what one more point does. I add a 4th surveyed point to the photo and ask each camera to explain it. 3 of them miss by 39 pixels, 165, 249. One camera stays at 0. That one is real. Today, why 3 points give you exactly 4 answers, and how 100 points give you 1. This problem has a name: perspective and point, PnP. You know the map, endpoints whose 3D positions are given in some world frame. You know the picture, where each of those points landed in the image. And you know your camera. It's calibrated, its intrinsic matrix K is known. What you want is the pose, the rotation R, 3 by 3, and the translation T, 3 by 1, that carry a point from the world frame into the camera frame. And this is everywhere. Every Aruco marker a drone lands on, PnP. A robot localizing against surveyed landmarks, PnP. Structure from motion registering a new photo into a half-built reconstruction, PnP, thousands of times. Here's the one sentence the whole video hangs on. The image gives you the angles, the map gives you the lengths, and the pose is whatever makes the two agree. Hold on to that. We'll earn it piece by piece. The plan, and it's 3 videos. This one is the minimal case, 3 points, and a solution from 1841, older than photography's first tripod. It ends with the 4 answers you just saw. Part 2 picks the real one out of the 4, and then finds the single place in space where the whole method quietly falls apart. It's a cylinder of all things. Part 3 is the modern half. Hundreds of points, noise, outright wrong matches, and the machinery that eats all of it. That's where Solve PnP comes from. So take whichever you came for. Want to know why 3 points give 4 answers and where that answer came from? You're in the right place. Stay. Need a pose out of a marker this afternoon, and you don't much care who Grunert was. Go straight to part 3. It's linked below, it starts from scratch, and the only thing it borrows from me is one sentence, which I repeat when you get there. None of these 3 is homework for the others. First, let's cash in the word calibrated. It's doing more work than it looks. The pinhole model says, a point in the camera frame gets multiplied by K, focal lengths fx and fy, principal point cx, cy, and divided by its depth. That's how 3D becomes a pixel. But K is a 3 by 3 matrix and it's invertible, so we can run every pixel backwards. Take the pixel, append a 1 to make it a 3 vector, multiply by K inverse, and out comes a direction. A ray leaving the camera center, passing through that pixel off into the scene. Normalize it to unit length and call it d hat. The point that made this pixel sits somewhere along that ray. We know the direction exactly. What we don't know is how far. One unknown number per point, the distance s along its ray. And here's a promise you can check. From 2 pixels alone, no 3D information at all, K inverse gives me 2 rays and the angle between them. In our running example, 19.35 degrees. Computed a second way from the true 3D geometry, 19.35, identical. That's what calibrated buys. The image hands you angles. From this moment on, the pixels never appear again. The camera is just a fan of rays. Before solving anything, let's count. How many numbers is a pose? 3 for the rotation, an axis, and an angle. 3 for the translation. 6 unknowns total. And how much does 1 point buy us? Each correspondence says, this 3D point must land on this pixel. A pixel is 2 numbers, a row and a column. So that's 2 equations per point. 2n equations against 6 unknowns. 1 point, 2 equations, 6 unknowns. The camera can be almost anywhere. 2 points, 4 against 6, still a whole family of poses. You can swing the camera around the line between the 2 points and nothing changes. 3 points, 6 equations, 6 unknowns. Now it can be solved. But 6 equations matching 6 unknowns promises finitely many answers. It does not promise 1. You watch that in the opening. 3 points, 4 perfect cameras. Where does 4 come from exactly? That number is about to fall out of the algebra, and it'll fall out looking inevitable. Keep one thing in your pocket for part 2. The count says 3 points can determine a pose, but the famous linear method will turn out to need 6. Same problem, 2 different minimums, and the difference between them is the whole story of this video. So, 3 points. Call them P1, P2, P3. The camera center C looks at all 3, and together the 4 corners make a tetrahedron. Let's sort its edges into what we know and what we don't. The base triangle, the 3 sides between the points, we know completely because the map gave us the 3D positions. Side A, opposite point 1. Side B, opposite point 2. Side C, opposite point 3. 3 known lengths. The 3 angles at the camera, the angle alpha between the rays to points 2 and 3, beta between rays 1 and 3, gamma between rays 1 and 2. We know those 2. That was the last section. Each cosine is just a dot product of 2 unit rays. Cos alpha is d hat 2 dot d hat 3. The image gave us the angles. What's left? The 3 edges from the camera to the points, the distances S1, S2, S3. Those are the unknowns, and notice what just happened. The rotation is gone, the translation is gone, no R, no T, no frames. The whole pose problem has collapsed to find 3 lengths. This is why the problem is older than photography. In 1841, Grunert solved exactly this for surveyors, standing in a field, sighting 3 church towers marked on a map, asking, "Where am I?" Same triangle, same angles, same 3 unknown distances. We've just swapped the theodolite for a CMOS sensor. 3 unknowns need 3 equations, and the tetrahedron hands them over 1 face at a time. Look at the face holding the camera and points 2 and 3. It's a triangle. 2 sides we don't know, S2 and S3, meeting at an angle we do know, alpha. And closed off by a side we know completely, A. Any triangle with 2 sides and the angle between them obeys the law of cosines, the Pythagorean theorem with a correction term for not being a right angle. So, S2 squared plus S3 squared minus 2S2S3 cosine alpha equals A squared. That's one face. There are 2 more just like it. Camera with points 1 and 3. S1 squared plus S3 squared minus 2S1S3 cosine beta equals B squared. Camera with points 1 and 2. S1 squared plus S2 squared minus 2S1S2 cosine gamma equals C squared. 3 equations, 3 unknowns, but look at them. Every one is quadratic, and every one shares its unknowns with the others. Nothing here solves by substitution in one line. Grunert's move, the 1841 move, is to stop chasing the 3 lengths directly and go after their ratios instead. Define two new unknowns. U is S2 over S1 and V is S3 over S1. How much bigger or smaller the second and third distances are compared to the first? Just shape information. A small tetrahedron and a scaled-up copy share the same U and V. Substitute S2 equals US1 and S3 equals VS1 into all three equations. And then divide each equation by S1 squared. Watch what that division does. Each equation can now be solved for S1 squared on its own. From the first face, S1 squared equals A squared over U squared plus V squared minus 2UV cosine alpha. From the second, B squared over 1 plus V squared minus 2V cosine beta. From the third, C squared over 1 plus U squared minus 2U cosine gamma. Three different looking expressions, and they're all the same number, S1 squared. So set them equal to each other, and S1 cancels out of the problem entirely. Two independent equalities, two unknowns, U and V, the pure shape of the tetrahedron. Solve for the shape first. The size comes back for free afterwards, because any one of those three fractions hands us S1 the moment we know U and V. Two equations, two unknowns, one elimination left. Cross-multiply the pairs, use one equation to express U in terms of V, push it through the other, clear every denominator. It's an afternoon of careful algebra, and Grunert did it by hand. What comes out the other side is one polynomial in V alone. A 4V to the fourth plus a 3V cubed plus a 2V squared plus a 1V plus a 0 equals 0. A quartic, degree 4. Every coefficient is built from things we already hold. The three side lengths from the map, the three cosines from the image. Here they are on screen. I won't read them to you, but I will tell you they're checked. Plug the true ratio V into this quartic and it evaluates to 10 to the minus 17. Machine 0. And one confession from making this video, my own notes had a parenthesis in a 3 in the wrong place, off by one bracket, and the residual screamed at 10 to the minus 4. The formula gets no vote, the numbers do. A quartic is the last polynomial degree with a closed form solution, so V comes out exactly, and each root unwinds all the way back down the chain. V gives U, there's a direct formula. U and V give S1. In our running example, 8.57 meters. Then S2 is U times S1, S3 is V times S1. Three distances, the tetrahedron is solved. And there it is, the promise from the first minute paid in full. 4 roots, 4 answers, not a bug, not noise, not a bad solver. The geometry of 3 points genuinely admits 4 camera poses, and the algebra hands you every one of them. The 4 cameras you saw at the very start were not a trick, they were this polynomial drawn. Which leaves the obvious question, and it's the whole of the next video. 4 answers, and you need 1. How do you tell them apart? And what happens when you're standing in the one place in space where the quartic quietly stops being able to tell you? That place is a cylinder, and a camera sitting on it loses about 100 times its accuracy. Part 2, picking the real one and where it breaks. See you there.